Hello chemists, this is Ms. Placino and you're watching Screencast 7.6 on gas laws. In today's lesson we're going to continue our discussion on how gases behave and teach you some new formulas to work with. So let's take a look at the do now. Describe your experiences with helium-filled balloons and carbon dioxide-filled balloons. What are they like new and what are they like a few days old? Take a second, pause the video, brainstorm a little. All right, hopefully you've had a helium balloon at some point in time, or at least seen somebody with one. Helium is less dense than air, so of course it floats. And when you have a brand new helium balloon, if you take it inside, you let go of it, it's going to float all the way up to the ceiling. You go to sleep, you wake up the next morning, and in many cases, especially if it's just like a latex balloon and not one of those kind of metallic mylar balloons, the balloon has shrunk. It's like deflated a little bit, and it's not floating nearly as high as it used to be. Maybe it's waist level or so. This is the case with helium. Carbon dioxide, on the other hand, is more dense than air. So carbon dioxide won't float. It's going to just stay on the floor or the table or wherever you put it. You go to sleep, you wake up the next morning, and it looks like essentially nothing has changed. The balloon hasn't deflated, at least not noticeably so, and it's still behaving exactly the way it was before. And you might wonder, well, why do my carbon dioxide balloons stick around for so long, but my fun helium balloons seem to deflate and lose their gas so much faster? And there's actually a formula we can use to figure out how much faster helium balloons would deflate than a carbon dioxide balloon. So let's start there. We're going to talk about rates of effusion and diffusion. Before we get into any math, let's clear up some terminology. So we'll start with effusion. If you look at the picture, you've got like little particles of gas. We've zoomed in on a balloon, and we got the arrows pointing out. So this is trying to show gas escaping. The rate that a gas escapes a container, something like a balloon, for example, through a small hole is called effusion. I know to us, you pick up a balloon and it doesn't seem like there are any holes in it. However, if you were able to see it on the microscopic level, you'd see that there are pores, and those pores are big enough to let gas molecules out. They're small enough so it doesn't happen immediately, but it is possible and the gas does escape. Diffusion. If we look at the before and after pictures before diffusion, we have a high concentration of these red atoms in just one location. After diffusion, they've spread out and we've made a homogeneous mixture. What is going on upstairs? Jeez. So diffusion is the spreading out of molecules away from a concentrated region. And gases will diffuse in other gases very, very readily. You'll always have a homogeneous mixture of gases, especially, even if you've kind of like released a new gas into a system, like we have like the red atoms in that before diffusion picture. If you give it couple of seconds, couple of minutes, depending on the speed that the molecule moves, the temperature that these substances are at, they're going to diffuse and become homogeneous. That still doesn't necessarily get us to figuring out the rates of effusion and diffusion. Before we do any calculations, I'm going to go back to the gas simulator for just a moment. All right, we've used this simulator before. If you look, we've got the temperature, pressure, and volume all staying constant. They happen to be at 400 K, 3.4 ATMs, and the volume's 580 liters. Kind of unimportant at this point in time. Inside the piston, we have small red atoms, we call those gas A, and we have larger orange atoms, gas B. Now, we had talked about this in a previous lesson, the speed of the gases. The temperature of a gas is directly related to its kinetic energy, and kinetic energy is equal to 1/2 the mass of the gas times the velocity, or speed, squared. If you just kind of eyeball it, hopefully it's pretty easy to tell that the red atoms are moving substantially faster than the orange ones. How about the frequency at which they collide with the walls of the container? Yeah, it looks like the red atoms are hitting the sides of the piston a whole lot more frequently than the orange atoms are. If you think about it, in order for a balloon to deflate, you need your gas particles to come in contact with the side of the balloon and hopefully hit with one of those little pores so it's able to escape. Just kind of based on statistics and probability, if you've got a molecule, or in this case atom, moving faster and colliding with the sides of the container more frequently, it's going to have a better chance of finding one of those pores and escaping. This is why we see helium balloons deflating so much faster than carbon dioxide balloons. The speed of the helium atoms at room temperature is going to be greater than the speed of the carbon dioxide atoms at room temperature as well. So let's see if we can put that to some math. When we go to calculate the rate of effusion or diffusion of gases, we're really trying to just compare which one is moving faster and how many times faster. It's all based on molar mass. We need to know how much that atom or molecule would weigh if we have a mole of it. This is the formula that we're going to use. The rate or the speed of substance A divided by the rate of substance B is equal to the square root, the molar mass of B divided by the molar mass of A. I know this formula can look a little intimidating with the square root sign, but I promise it's not too bad. One thing to make note of, a common mistake, we've got A in the numerator on the rate side, and then it gets flopped into the denominator on the molar mass side. So just something to really kind of make a note of. They're going to be like diagonal from one another, not directly across the equal sign. We know that lighter molecules move faster than heavier molecules at the same temperature. So it's going to be easy for us to know if we have the identity of the gases, all right, which one's moving faster, which one's moving slower. That's just which one is heavier, that's the slower one. And when we're solving these problems, it's really helpful to make one of the rates equal to 1. And we're going to go through an example problem so that you can see what I mean. Well, let's take a look at our hydrogen, did it again, our helium and carbon dioxide balloons. So I'm going to set it up where I've got the rate of, I'll put helium, in the numerator, the rate of carbon dioxide in the denominator. Technically, it doesn't really matter which one I put where. I've just arbitrarily chosen to put helium in the numerator and CO2 in the denominator. You can flip this upside down and you can still arrive at the correct answer, because we're just comparing their relative rates. I have helium in the numerator on the rate side, so does it go in the numerator or the denominator on the molar mass side? Hopefully you're thinking the denominator, and helium has a molar mass of about 4 grams per mole. So go ahead and plug that in the denominator. Carbon dioxide, it's only got one other place to be. It's going to go up in the numerator, and the molar mass of carbon dioxide is about 44 grams per mole. All right. I personally think it's easiest to take things out of square root and put them into like decimal form, but it's really up to you. So I can really set all of this equal to the rate of helium divided by the rate of CO2 is going to be equal to the square root of 11. Again, I have the tendency to take it out of square root format and make it a decimal. And I use my calculator, I get about 3.32. Which one of these is going to move faster, the helium or the carbon dioxide? Well, definitely the helium because it's lighter. So I'm going to set the rate of carbon dioxide equal to 1. So I've got the rate of helium is equal to the rate of CO2. Sorry, that looks messy. Times 3.32. And I'm going to set the rate of carbon dioxide equal to 1. I'm just trying to see how many times faster helium should be moving as compared to CO2. And I end up with just the rate of helium is equal to 3.32 times as fast as CO2. These questions can become fairly complicated, but at this point in the game, we're going to try to keep it relatively straightforward. You've got a couple of practice problems to work with in your workbook. I highly recommend giving them a shot. All right, let's move on to what I think is a much easier gas law. The law of partial pressures. So in this case, I've got oxygen, nitrogen, and then a mixture of oxygen and nitrogen. According to the law of partial pressures, if you have a mixture of gases, the pressure will be equal to the sum of the pressures of the individual gases. It turns out the identity of the gases do not matter. So just to go through and do a practice problem, if I've got oxygen with a pressure of 159 millimeters of mercury, and my pressure of nitrogen is 593 millimeters per mercury, if I want to figure out what the pressure would be if I combine those two gases, it's really just as simple as adding them. So in this case, the pressure of that mixture would be 752 millimeters of mercury. One thing to just kind of keep track of, make sure that your units for pressure are the same. That's really the only way I can make this more complicated, is to give you like millimeters of mercury in atmospheres or kPAs, and that way you'd have to convert. But it always works out that the pressure of one gas plus the pressure of a second gas, let's say I throw another gas in there, what do you think I'd do with that? Yep, I would add that as well, plus P3 plus that, as many gases as you have are going to be equal to the total pressure. Definitely an easier one to deal with than rates of effusion and diffusion. The last one I want to talk about today is calculating the density of a gas. Hopefully you remember from earlier in the semester or a previous science class, the density is equal to mass divided by volume. We're going to assume that the gas is at standard temperature and pressure, and also that we just have a mole of the gas. If I assume that I have 1 mole of gas at standard temperature and pressure, I should be able to figure out what the volume of that gas would be. We talked about it during stoichiometry a couple units ago, actually just 1 unit ago. At standard temperature and pressure, every gas, regardless of its identity, occupies 22.4 liters of space. If I have a mole of that gas, I'm going to be able to calculate its molar mass. Let's use oxygen, for example, if I want to find the density of O2. I know that oxygen is 16 grams per mole, times 2 of them gives me 32 grams per mole. And if I take my, it's going to let me right up here, maybe over here, 32 grams per mole, and I divide it by 22.4 grams per mole, sorry, 22.4 liters per mole, misspoke. I can do the math real quick. And in this case, I come up with, well, I've got 2 sig figs, although technically none of those are measured, so it's not super important. 1.4 grams per, careful, liters. Often you'll see the density of gases expressed in grams per liter. This way you don't end up with numbers in scientific notation or a whole bunch of leading zeros. That's just something that's pretty standard across the board. So at standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius, oxygen should have a density of roughly 1.4 grams per liter. All right, well, that wraps it up for today. You've got a lot of problems to practice with. Make sure you feel comfortable using the formulas, especially the rates of effusion and diffusion. I know that one can be tricky. All right, thanks for tuning in, and I hope you found this helpful.